Okay, so there is going to be a particle motion FRQ on your AP test. We've now seen about like 3 of the types of FRQs, 3 out of the 6 that like you're pretty much guaranteed to see. We'll see another one in F. We'll see another one in G. But I mean, really, if you do enough practice on these FRQs, you start seeing what they ask. You know what they ask, and you know what to do every single time. So we've talked a lot about particle motion. We've answered most of the questions that they would ask us. The only piece that was missing was the actual integral. So before the integral, if they gave you velocity, there was no way to work your way back up to position. Why don't you do this with me instead of copying answers on an FRQ, which does nothing for you. Yeah. So anyway, back to my thought. So, that's the one thing we couldn't do in any of our problems was work our way back up to functions that we've taken derivatives of, but that's what integrals allow us to do. So there really are 3 main types of integrals that you'll see with particle motion. And the 2 of them are the same as what we learned when we were doing just general context problems. So if the first one is just integrating your velocity function, just like any other context equation, velocity is going to be measured in some sort of distance per time. So let's just say meters per second, right? If you integrate meters per second, your label is going to be meters, right? Yep. Which means that it's going to tell you how much those meters have changed, which we consider displacement, right? It answers the question, how far did I move from my starting value? And that displacement is going to have a sign. Positive is going to mean you've moved to the right. Negative means you're going to move to the left. It doesn't tell you anything about how that happens, though. Moving 3 units to the right could just be moving 3 units to the right. It could also be moving 100 units to the right and then another 97 back to the left. So that's the one thing we don't get with displacement. We just know I knew where I was, and this is how far away from that I am. How I got there, nobody knows. The displacement on AB, according to the graph on the left, is basically you would just do the same thing we would do. This is just basic integrals. I would do A1 minus A2 plus A3. And that's under the impression that A2 is a positive number. So I think it says it says A1 and A2. Assuming all of these areas are positive, to figure out this integral, you would add the area that you figured out for A1, subtract the area for A2, and then add the area from A3, and that's nothing new, right? That's just how you figure out an integral. The kind of just going straight down from that one, displacement is how far you moved. If you want to know where you're actually at, you need a starting position, right? So if you want your actual position, you just take your initial position and add the integral to it. So this would be the same thing with a C plus at the beginning of it, A1 minus A2 plus A3. Keeping in mind that whenever you set an integral up like this, regardless of whether you're in just a generic context question, just a calc problem that doesn't even have any story to go along with it, or particle motion, the number you're starting with is the value of your function at the start of the integral. So C is x of a. I have that up at the top. Those 2 things should always match. Your function value at a plus the integral of its derivative from a to wherever you want to end. This is kind of locked in stone. And if you understand that, this is always how your integral should be set up. And then, of course, with this, the third integral, the one on the left, is kind of the one that kind of is different. Like, we don't really have this one in our other story problems, but it does make sense in the context of particle motion. There's a big difference for me just moving 3 units to the right versus me moving 100 units to the right and then 97 back to the left. And that's what our final integral is for, which is the total distance traveled. In that case, I wouldn't say I moved 3 units. I'd say I moved 197 units. I didn't get very far because my displacement was only 3, but I did do the full 197 units of moving. And to do something like that, and kind of to remind you about what it means to integrate an absolute value function, we just consider all of our areas above the curve instead of below them. So this function right here takes the A2 section and mirrors it over there, and that's really what you're integrating. But in the end, it's just A1 plus A2 plus A3. Okay, so let's do an example of just those three questions. So our example one, a particle is traveling on the x-axis with the velocity given by the velocity function. And we want to know how far it is from its original position after 9 seconds. I don't know where it started. I can't figure out where it's ending because of that, but I can figure out just how far it's moved. Or not how far it's moved from its original position. And I do that just by integrating. So we'll do the integral from 0 to 9 of t squared minus 2t minus 3 dt. So that feels like t cubed over 3. I think we'll use a calculator for this one. Minus t squared minus 3t. Agreed? Plugging 0 into that is going to give us nothing at the end. I'm going to end up not using a calculator, even though I said I was going to. So we just need to plug 9 into all of this stuff. So this ends up being 9 cubed over 3, which actually isn't too bad to figure out, minus 9 squared minus 3 times 9. What I would do instead of 9 cubed over 3 is I'd only do 9 squared. And then I've got a 9 divided by 3. So I'd take 9 squared and multiply that by 3. Make sense? Is that what? So that's 81 times 3, which is not too bad in the head. 81 times 3 is 243. 3. Yeah. I thought I heard a 244. Did I get you 244? Or did I just... You guys were whispering, so yeah. I don't know. Anyway, gotcha. You forgot to do the... Wanted to do the wrong answer? Oh, okay, gotcha. All right, anyway, well, whatever. Either way. So then we're going to do 243 minus 81 minus 27. It's probably a way to do this. Probably should just factor the 9 out of the whole thing to start out with. That would have made life easier. Why don't I just do this? 9 times 9 squared over 3 minus 9 minus 3. It's going to be easier. And the minus 0 is gone. So that's 9 times 27 minus 12. Yeah. Equals 9 times 15, which is 135. Cool. Yes. Letter B says, how far did the particle travel in the first 9 seconds? This one's a little bit more work because we actually have to do the figuring out of when did it travel to the left and when did it travel to the right. And we've got to take those and integrate them separately and consider everything as a positive value. If we integrate and get positive, then we'll keep that number. If we integrate and get negative, we'll keep that number. So what we're doing here is the integral from 0 to 9 of v of t dt, instead of writing it out. Sorry, absolute value of v of t dt. Which means we've got to figure out when this thing is traveling left and when this thing is traveling right. Sign chart. Sign chart for what? Which function? V of t. Velocity. The sign on velocity tells you direction. So if you need to know whether it's going left or right, velocity is the thing that tells you that. So we've got t squared minus 2t minus 3 equals 0. That factors to t minus 3 and t plus 1. Agreed? Which means we've got a t equals 3 and a t equals negative 1. But we have a domain 0 to 9, so we don't care about t equals negative 1, correct? So we'll do our sign chart. We'll start at 0, we'll end at 9, we'll hit at 3. And we will consider both signs. So t plus 1, that is always going to be positive. I don't know why I did that one first. It's the second one there. So t plus 1 is always going to be positive. That felt like the one I was going to have to think harder about. And t minus 3 just follows the normal minus plus. So our particle started out moving to the left and then ended up moving to the right. So that integral, the absolute value from 0 to 9 v of t dt, is actually equal to the integral from 0 to 3 of v of t. So I'll do t squared minus 2t minus 3. Plus the integral from 3 to 9. So once you split it, you just, those absolute value bars, I don't care whether I get a positive or a negative out of that integral, because it's telling me I moved either to the left or to the right. So I just need the positive values of them. It's not the only way to do it. I could actually just multiply a -1 into that first integral. That first integral is going to give me a negative. That second integral is going to give me a positive. All right. All right, so let's do some math. There's only one number that we don't know here, and that is going to be our integral evaluated at 3, right? So we need to know what's that? Because we know what we get when we plug 0 into the antiderivative, and we know what we get when we plug 9 into the antiderivative. And the only number we need to plug in is 3. So in the interest of saving space, t cubed over 3 minus t squared minus 3t evaluated at t equals 3 is -9 according to Joseph. Yeah. So let's see, we've got 9 minus 9 minus 9. Sounds like -9 to me. Okay. So then back to orange, that gives us absolute value of -9 minus 0 plus the absolute value of 135 minus -9. So yeah, so we ended up, it seems like we traveled a total of 18 more, because this ends up being 9 plus 144, which is 153. I don't know why my brain wouldn't brain on that one. Cool. So yeah. Which kind of this should actually kind of make sense to you, what we figured out here. We figured out from time 0 to 3, our particle traveled 9 units to the left. So then to go a total of 135 to the right, it had to go those 135 to the right, and then it had to make up the 9 that it went to the left. So that actually does, when you think it all through, kind of makes sense there. So that's actually why we ended up using the 9 twice. It got used here because it was going to the left, and then we had to make that 9 up over here. And then probably the easiest question on the page, if the particle started at x equals 10, at what location was the particle at t equals 9? Well, that's just going to be 10 plus what we did in example A, 10 plus 0 to 9 of v of t dt, which we know to be 10 plus 135. So you can see which one's the most work, right? When they want total distance traveled, you've got to do a whole lot more, because you need to do the sign chart. You've got to do it on the correct function, which is velocity. And then you have to break up and do 2 integrals, and then just basically don't care about what sign you get when you get those integrals. If it moved 9 to the left, it moved 9 units. If it moved 144 to the right, it moved 144 units. Questions on any of that? All right. Okay, so this table on the next page represents a good reference for just about, I don't want to say everything, but most of the standard things being asked. So you may have a question. That's the left column. The middle is kind of just the thing that you need to do. So for example, with number 1, the way I fill this chart out, the times when the particle is stopped, the particle being stopped is equivalent to saying that v of t equals 0. If you said x of t equals 0, you'll probably get the wrong answer. If you said a of t equal to 0, you will probably get the wrong answer. Know your function. If the particle is stopped, it's velocity. Don't use pronouns. Don't say it's 0. That's a good way of telling me you haven't fully thought about the question. So to solve that, you need to find v of t if necessary. And then set it equal to 0. That's what we did in the middle question on the last page. It wasn't what they asked us, but we had to figure out when it stopped because that's when it changes directions. Oh, I understand. Yeah. This is me stealing from other material. Instead of particle, this person wrote bug. Sometimes the question is written as a bug instead of a particle. But if something, whether it's a bug or a particle, is moving to the right, that means the velocity is greater than 0. I don't care what the acceleration is. I don't care what the position is. I care what the velocity is. If it's moving to the left, bad job of copying and pasting, v of t is less than 0. And then the time when it turns around, well, then that v of t has to change signs. These are direct analogs of things we do with normal problems. V of t is the derivative. It is the derivative of position. So this is equivalent to saying that the function x of t is increasing. This is equivalent to saying x of t is decreasing. And this is equivalent to saying x of t has a relative extrema. I don't care if it's a relative min or a max, but if it has one of those, it's changed signs. No, we don't have anything. We barely have half our class, let alone money. They'd have to be here to give us money. Anyway, that was Make-A-Wishing for anybody listening to the video, wondering what's going on.
I donated to another class.
Oh, well.
No,
Yeah.
he was at 59. I put $1.
All right.
Oh yeah, that would be fun.
Okay, so kind of similar thing here. We need to find v of t if necessary. I write that just in case you just start doing the problem with the wrong function. Set equal to 0 or undefined. That's usually more if you're looking at a graph. You can't really set it equal to undefined, but if you're looking at a graph instead, you're just looking for those zeros or you're just looking for where it's undefined. And then make a sign chart. These are all the things you would do for increasing intervals, decreasing intervals, or relative extrema. So a lot of particle motion is just vocab. It's different vocab to tell you to do the same thing. The next one doesn't necessarily, I mean, you could definitely ask these questions about other contexts. We just don't see them as much. Are the bananas being taken off the table at an increasing rate is kind of the same thing as saying, is the particle speeding up? So they could be written in those contexts, but they just make the most sense in particle motion ones. For speeding up and slowing down, this is the one where we look at v of t and a of t and check to see if their signs match. So speeding up, v of t and a of t have the same signs. Slowing down is the opposite. And we talked about this the first time we did particle motion. If you're already traveling to the right, positive velocity, and your acceleration is being pulled in the right, towards the right, that is going to speed you up. Likewise, if you're already going to the left and then acceleration is pulling you even more to the left, that's going to speed you up. So same signs is going to speed you up. Otherwise, if those signs are a mismatch, you're going to be slowed down. In order to accomplish this, you need to find v of t and a of t. Maybe one's given to you. Maybe you have a graph of v of t that you can read points off of, and a graph, and then looking at looking at the slopes of whatever's on your graph will tell you what a of t is. But you have to know what v of t is and a of t is, and you need to get those values. Plug C in and get values. So, again, plug C in if you have the function itself. Again, you may be reading from a graph. Plug C in and look at the values. And then the rest of this table is the new stuff we learned on the previous page. So the displacement of our particle, how far away from the starting point, and that's the integral of velocity. Directly related to that, but the actual location of the particle, I feel like this needs no translation. When you take x of a or s of a, whatever your position function is labeled at, if displacement tells you how far you moved, just take where you were and add or subtract that, whatever the sign is, and that'll tell you where you are now. And then, of course, total distance traveled. This is the one that's the most work. It's the total number of units moved, regardless of direction. The setup, which is important to know because sometimes they'll just ask about that, is integrating the absolute value of the velocity. But there's a lot of work to do here. You need v of t if you weren't already given to it, and set it equal to 0. And then integrate from a to b by intervals. And those intervals are directly related to where you found the zeros, right? I mean, I feel like I could write a paragraph to actually explain that out. And then you need to take the absolute value of each result. Find the zeros, break it up into intervals based on those zeros, integrate, and everything's positive. If you that integral is telling you how many units you've moved to the left or the right. So take the absolute value of it because we don't care,